Hello friends, in this lecture we will discuss about Euclidean inner product in Rn space. For that I will recall and you are knowing about vector space, moreover real valued vector space, and from this vector space we will try to extend our Euclidean space. Now for this Euclidean inner product space, what we need prerequisite, we will try to recall this prerequisite. Here, this geometrically what is the Euclidean space and how they are forming this Euclidean space, we will discuss. Moreover, first of all, Euclidean space, and we are finding their properties and how we are getting this Euclidean norm and all these things we will discuss here. First of all, I will recall here by taking R, this R as a field for real number when we are using vector space, and here we are using R as a real value, and this is a real number, and this is a real field, and then defining this Cartesian product R is to n space as R cross n times, and from this when we are taking element from this R is to n space, then we are getting n-tuple form. Means here, suppose I am taking x is element from R is to n, then we are getting x as x1, x2, and so on up to xn. Now here, this first x1 is from our first set, x2 from our second set, xn from our this last nth. Now here, this x is nothing but x having n coordinates. That means x is in n tuple, and remember that if any point having coordinates, then this point represents a vector. Therefore this x is called point. If point is there, then we can talk in terms of position vector. Therefore this is a point or this is a vector. Henceforth I am saying that, or we will call this x from R raised to n, means any element from R raised to n as a vector, and these coordinates, all these coordinates x1, x2, xn up to xn, all these are the from this Cartesian product. That means this individually from this R, means all these x1, x2, xn, these are the real numbers. Got it? Here any number if we are taking from R raised to n space, then this is our vector, and all these coordinates are the real numbers because we are taking the real field. Okay. Then next part, how we are taking addition of elements from this R raised to n space. Now this is x and y, mean these are the two vectors from R raised to n, and a is any scalar. Means here if we are taking R raised to n, these are the vectors, and elements from this set are only, and these are the scalars. And these are the vectors, and elements from this R field, these are the scalars. Now here how to take addition, multiplication of these vectors. This is our x and this is y, these two vectors. Means here x vector means I am representing here by these coordinates, and y vector is here by this coordinate. Means here this is your first vector, this is your second vector. When we are taking addition of these two vectors, then we have to take addition coordinate wise. This is the n tuple vector, this is again n tuple vector. Then we can take addition, and addition in this way. This is first coordinate plus first coordinate. This is coordinate wise addition. Second coordinate plus second coordinate, and so on. Last n coordinate, and here is n coordinate. And then we are getting addition in this way. This is x1 plus y1, x2 plus y2, xn plus y. Now this is just like vector, we are knowing vector addition and vector subtraction. Same thing is here. You can take add or you can take subtraction again, and you can subtract this. Now when any scalar is multiplied with this vector, then just we are multiplying by this scalar to this vector, the complement goes on increasing here. Or we can write this is equal to a1x1 plus a2x2 plus a3x. Now here minus sign, when we will multiply by x to by minus sign, then we have to multiply by minus sign to each and every coordinate to this vector. Now this zero vector, what is meaning of zero vector? Zero vector means zero having n coordinate. This is in coordinate system. That's why we are saying that this is a vector. And this individual zero here, in this coordinate, all these individual zeros are nothing but our scalars, because all these zeros are from this R. So this is a scalar. This single zero is scalar, but if we are taking this zero, this is vector, because this zero having coordinates, all these coordinates. Therefore, this is a vector. Now, after this, we will go towards our main article, that is inner product. Now, we are knowing about dot product of three-dimensional space, means I, j, k containing, our vector containing I, j, k. Means here, if our vector is in three coordinate form, three tuple form, then we can write its dot product. But instead of these three coordinate or three tuple form, we'll extend this idea to n tuple form. Here this is n tuple means x and y. These are the elements from R is to n. Therefore, this is the n tuple form. And then we have to take its dot product. To take its dot product, we can write this dot product as x bar dot y bar, and new notation is there, this notation, and this notation is called inner product. Now keep in mind, inner product is nothing but a dot product. And we are knowing that when we are taking dot product of any vector, then we are getting this is a scalar number. Therefore, this inner product is a scalar number. And here we are getting scalar from this. Then we can take dot product of this. Again, how we are taking dot product? First component into second component. First component of this vector into first component of this vector. Second component into second component. We are taking multiplication coordinate wise. And then we are adding all these. Here, this is our x1, y1 plus x2, y2 plus so on, x and y. Now we can write in symbolic form in this decimation x, I varying from 1 to n. Means here this is x1, y1, x2, y2 and x and y. Therefore, I am taking I and j. I here index, and this is in short form. Again, this inner product we can define in matrix form again. In matrix again, if you are taking column vector, then this is your first vector, but in matrix we can say that this is our column. And here x1, x2 and so on, xn, and y is equal to y1, y2, so on yn. This is the transpose of this. Now here x bar dot y bar, and this is the inner product of x bar. Now here I am taking x transpose into y. Now here is x is given in this way, and if we are taking transpose of this, and we are knowing that transpose of transpose is same vector itself. Therefore, this same vector itself into this column vector. This is a row vector into column vector, and we know how to take matrix multiplication. This x1, y1 plus x2, y2 plus x3, y3 and so on. We are getting same answer. But this is in notation is changed, this is in matrix. Now here, we can take dot product of same vector itself. This is just like b bar dot b bar, c bar dot c bar, a bar dot a bar, and we are getting this is a magnitude. A square is nothing but a bar dot a bar. In the same way, we can write here x bar dot x bar. Now this is inner product of x. We can read this as the inner product of x. Then we are getting here, this is x1 square plus x2 square plus so on, xn square. Now from this, we can talk or we can find magnitude. This magnitude is nothing but mod of a bar, or this is norm now. Henceforth, we can read this as a norm. Norm is nothing but magnitude of this. This norm is nothing but under root of or magnitude of a bar. How we are finding magnitude of a bar? This is a1 square plus a2 square plus a3 square. This is in 3D. But we are taking all these elements from Aristotelian space. Therefore, we are talking here about norm. And this is called Euclidean norm. This Euclidean norm of this x vector is under root of x bar dot x, or this is under root of this inner product, and which is nothing but x1 square plus x2 square plus all xn square. Means means here this is only generalization of our dot product in RSTN space. Now here we will define inner product space. An inner product on a real valued space V is a pairing that takes two vectors. Suppose we will take here V and W, these are the two vectors from this vector space V, and produces a real number. Now remember this is a dot product, and dot product is always a scalar, and scalar, all these numbers are scalars from R set, therefore this is a real number. Inner product is a real number. Now this is, here we are taking real number because we are taking this field as a, this is real vector space, that's why this is a real number, and we are getting this is a real number. And when we are saying that this is a notation for this inner product space, and how we are defining this, this is a notation for this inner product space, and this satisfying following three axioms. And for that I am taking, suppose U, V, W, these are the elements from V. Now what is V? V is a real vector space. This is a real vector space, and we are choosing alpha and beta, these are the scalars. Scalars means these are the real numbers from this R, because this is a real vector space, therefore field is R. Therefore alpha and beta we are taking elements from this R. And what is our dot product, or this is called inner product. Now henceforth I am reading this as inner product. Inner product of UV is nothing but dot product. U, we are knowing U having coordinates as U1, U2, U3 for Un, and V having coordinates as V1, V2, V3 for Vn, and then we can take its dot product U1, V1 plus U2, V2 plus on Un, Vn, and this is in summation. Now satisfying the condition, then this notation is called inner product, and satisfying following three conditions. Number one, linearity. This linearity is alpha, inner product of alpha U plus beta V W is equal to alpha into inner product of UV plus beta into inner product of VW. This is the linearity property. Or we can write in this way also. U into inner product of U and alpha V plus beta W. Then we can write this as alpha bar into UV, inner product of UV, plus beta bar into inner product of UV. Now why this is alpha bar? Because we can write this inner product of U and alpha V, and when we are taking this alpha outside this inner product, then from this coordinate, means from this V, then alpha is a scalar with V. When we are taking this outside, then this becomes a bar, alpha bar. And again we are using only this condition, and instead of alpha bar also we are using alpha, because we are taking real vector space. Means in real number, conjugate of that number is again same number. Therefore we are not using here alpha bar, because we are in a real vector space. Now symmetry. Now in symmetry is the inner product of UV is equal to inner product of VU. And here positive definite property is that for any U belonging RSTN, U is a vector from RSTN, then inner product of U vector itself is always greater than equal to 0, and if inner product of UV equal to 0, then U is equal to 0. Means if this satisfying V all these three conditions, then this inner product is called, this inner product equipped with this vector space, then this is called inner product space. Defining this inner product with our given vector space, then this is called inner product space. Now here this is the definition, and this is very easy one. Only taking dot product we will get here all these properties of inner product. Now here I will write some note for this inner product. Inner product of this vector space V with field F, and V and W we take elements from this V. Moreover, U is also there. U, V, W, all these elements from V, and we are knowing that this is our real number. We can write here inner product of U, V plus W. Then we can write in first inner product with respect to V plus inner product with respect to W. This is first inner product with respect to V V, then W. Alpha U and V, inner product of alpha U and V is nothing but, you can take alpha outside, means in linearity property we have discussed, but I am taking here separately. If alpha is here with U, then you can take alpha outside, but alpha is here with the second vector, then we are taking this alpha as alpha bar outside. This is alpha bar into U. This alpha bar means conjugate of that. Now if we are taking inner product with zero vector, then we are getting this is 0, or in this way also 0 into inner product of any vector is equal to 0. Now this is a scalar 0, but this is a vector 0, remember this. Again here we are knowing dot product of any two vectors, a bar dot b bar. A bar dot b bar is a b cos theta. A and b, these are the magnitude. Here is also same thing. U bar dot v bar, these are the two vectors. U bar dot v bar is equal to inner product, we can denote inner product. And what is definition of dot product? This is magnitude. Instead of magnitude, we can read now norm. This is norm of u into norm of v into cos theta. What is cos theta? This is cosine angle between these two vectors. Now this is the, again, in terms of inner product, we can define it. Inner product of uv is nothing but norm of u into norm of v into cos theta. Now here we are knowing that property of cos theta. Cos theta is always less than equal to 1. Magnitude of cos theta or modulus of this cos theta is always less than equal to 1. Therefore, we are getting this inequality. Magnitude of inner product of uv is always less than equal to norm of u into norm of v. And this is famous identity known as Cauchy-Cox inequality. This is Cauchy-Cox inequality. Next time we are using this when we will solve some problems, and we will prove this Cauchy-Cox inequality by another way also. Now here I am taking one example, and then we will go towards our next article. Now for this example, I am taking 3 tuple coordinate system here. U is here 1, 0, 1. V is here, means here U having coordinates, V having coordinates, and W having coordinates. Instead of this equal to, when they read U having coordinates, V having coordinates, and W having coordinates. Now first we will find inner product of UV. Now how to find inner product of UV? That means only we have to take dot product in between U and V. How will we take dot product? When we will take dot product of U and V, we have to take multiplication of first component into this first component, plus second component into this second component, third component into this third component. Here we have to take dot product of these two vectors, and we will take dot product here. First component into first component, and second component into this second component, and plus third component into this third component. And if we are taking here multiplication, this is 1 plus 0 plus 3, this is 4. Since we are getting inner product of UV is equal to 4. And keep in mind, inner product is always a scalar, and here this is a real vector space, therefore this is a real number. Here this is a real number. Now inner product of U itself, that means here we will find dot product of same vector itself. Is nothing but we have to take dot product of same vector. Again, how we are taking dot product? We have to take multiplication coordinate lines. Here, this 1 into 1 is 1, plus 0 into 0 is 0, plus 1 into 1 is 1, and this is your 2. When we are knowing here the inner product of two the same vector itself, then we can find its norm easily. What is norm? Norm of U is equal to under root of inner product of this vector itself here, and this is equal to 2. Already we are knowing this, therefore this is under root of 2, and this is norm of this vector, and find norm easily. Then we have to find out inner product of 2U plus 3V and W. All these terms, all these coordinates are known, therefore we will write here this as, first we will try to find out this 2U plus 3V. What is 2U plus 3V? This vector 2U, 2 into this U, coordinates of U, plus 3 into coordinates of V. I will multiply 2 to this coordinate, therefore we will get 2, 0, 2. I I will multiply 3 to this coordinate, we will get 3, 6, 9, and then we have to take addition. How we are taking addition? We will take coordinate wise addition because we have to add here these two vectors, and we will get here this is 5 plus 0 plus 6, 6, and here 9 plus 2 is 11. We are getting this is addition of this vector. Now we have to take inner product of this vector with W, and here this is inner product. Inner product means we have to take this vector dot product with omega or W this vector. This is vector, and we will take here dot product. Dot product means again coordinate wise multiplication. 5 into 3 is 50. 6 into 6 is 36, and 11 into 9 is 99. If we are taking addition, then we will get this answer. Same thing is here. Instead of plus, I am taking here minus. You can go through this answer and try to find out your answer. First of all, we have to find out 2u minus 3v. We will find 2u minus 3v. This is 2u minus 3v, and when you calculate this, you get this is 2u minus 3v. You should go through this carefully. Now we have to take dot product, means here inner product of this vector and omega vector. We will take dot product of this result with omega, and simplifying this, we get here results. Okay, practice for such a type of examples, and you will get again meaning of this inner product. Now here I will take next example, and we will try to prove this, is it inner product or not. We will prove this, and this inner product is defined by inner product of uv is equal to u1 v1 plus u2 v2, where this u is u1 u2 and v is v1 v2. Means u having coordinate u1 u2 and v having coordinate v1 v2. That means u and v, these are the elements from R2 space. And this is our definition of inner product. Means dot product of u and v. U is given, v is given, u having coordinate u1 u2 and v having coordinate v1 v2. That is, we will try to prove this is inner product. Now, what is meaning of inner product? Inner product means this satisfying three conditions: linearity, then symmetry, and we have to show that this inner product of u and u is always greater than equal to 0, and if this is 0, then u must be 0. That is, we will try to check. This is our u, this is v, and this is w. We are taking three vectors from R2 space, and alpha and beta, this is our real number, or both are the real numbers, and we will check for first condition, linearity. I will take alpha u plus beta v inner product with w. This is equal to, now I will write here alpha u and beta v. What is alpha u plus beta v? Alpha u plus beta v, that means this is alpha u plus beta v. This is alpha, this is our u, and this is our v. Then we will take here these two vectors, and when we will multiply by alpha, then this is alpha u1 plus beta v1, here coordinate wise addition, plus alpha u2 plus beta v2. Are you getting this? This is your u vector, this is your v vector. We are multiplying by alpha to u and beta to v, and then we are taking addition, coordinate wise addition, and then we are getting this coordinate wise addition. And we have to take inner product with w, that means we have to take dot product with w. Now we have to take dot product. How we are taking dot product? This is your first component into first component, second component into second component, and then we are taking addition. This addition is here in this. This is your first component into w, second component into w2. Now here I am multiplying by this alpha u1 into w, beta v1 into w1, alpha u2 into w2, beta v2 into w2, and here this color, blue color containing alpha, here also this color containing alpha. Now this pink color containing beta, here also containing beta. I will combine these with alpha term and with beta terms, and I am writing this way: alpha into u1 w1, u2 w2, and beta into v1 w1 plus v2 w2. Now u1 w1 plus u2 w2, this is here. u1 v1 plus u2 v2 is the inner product of uv. Therefore, this is nothing but inner product of UW and V1 W1 plus V2 W2. Surely, as per our definition, this is nothing but inner product of VW. Therefore, I will write this is inner product of UW and this is inner product of VW. Means here we can write this as alpha into U omega plus beta into V omega, and this is our first property, linearity, and linearity hold. Now second property, symmetry, we have to prove. Means inner product of UV is equal to inner product of V, we have to prove this. Now as per our definition of this inner product, as per given here, I will write. Now here, this is the simple our usual multiplication. This is U1 V1 plus U2 V2, and I will write this multiplication as V1 U1 plus B2 U2. Now here, this is V1 U1 plus B2 U2 is nothing but inner product of V and U. This is nothing but inner product of V and U, and this is your symmetric property. It's first linearity hold, symmetric hold. Now third property. For third property, I will take inner product of U and U itself. And we have to prove that this is greater than equal to 0. Now let us check. As per our definition of inner product, U into U itself, therefore this is U into U1 plus U2 into U2. This is nothing but U1 square plus U2 square, and we are knowing that square of real number is always a positive number. This is always a positive number because this is square. Positive plus positive is always positive number, therefore this number is greater than equal to 0. That means inner product of U is always greater than equal to 0. Now second condition. What is second condition? If inner product is 0, then we have to show that U is equal to 0. Now I will take suppose for this inner product is 0. This inner product is 0 means U dot U equal to 0. And again U dot U equal to 0, that means U equal to 0. Or you can write here, this is equal to 0. Dot product is 0 means this is equal to 0. Square this term plus this term equal to 0. That means here, both term we can take this is equal to 0 and this is equal to 0. And from that also we are getting this U equal to 0. Okay? So all these three conditions are satisfying as per the definition of inner product, and hence this definition defined by the inner product UV, U1 V1 plus U2 V2 is the inner product. Okay. Now after this we will discuss all remaining problems. Now okay, thank you.